and v. Basically, let's suppose that you fix x1 equal to 0, and then the resulting figure here could be, for instance, like this. This would be the projection, the intersection of the resulting surface, because the value of the benefit for varying x1 and x2 describes a surface here. And if you fix x1 equal to 0, you get the intersection of the surface here, and this is the maximum value of the surface that you would find. But this maximum here, it would be impossible to find with an overall minimization of the resulting surface, because maybe that this benefit here, if one went in this direction, is still increasing. So by minimizing the overall derivative of the Lagrangian, you don't find this point here. You find it only if you put x1 equal to 0, and then of course you get this function here, which has a maximum. But this maximum is identifiable only if you put x1 equal to 0. If you allow x1 to vary, then you don't find this maximum. Because if x1 is varying, maybe that it's increasing for increasing x1, increasing for increasing x1. It's not the top of a mountain in the surface. It's the top of a mountain only if you fix x1. But if you allow x1 to vary, this is not the top of the mountain. Then the surface may look like this. And then the same thing if you fix x2. If you want to fix x2 here, then you may get here a surface that is done like so. So depending on the value that you fix for one of the two decision variables, then you find for the corresponding curve, which is the intersection of the overall surface with the given value of x1, you may find an optimum. But only if you fix a value. You know, I understand that to write a sketch in 3 dimensions is not easy, but the moral of the story is that when you have two variables, you have to fix the extremes one at once, and then for each time that you fix the extremes, the boundaries, you have to perform a minimization of the remaining objective function, which is much complicated. So think if you have 5 allocations, it becomes, you know, it becomes quite a mess. So this is the second drawback, the need to check the boundary conditions, which implies a lot of work, a lot of practical work. Okay. Now let me turn to a more interesting, another drawback, which is intuitive. You have seen that for taking a constraint into account, I have to introduce a dummy variable, lambda, a virtual variable, lambda. And I have to introduce one more derivative than in the optimization procedure, one more equation. So the moral of the story is that for each constraint that you introduce, you have to introduce an additional dummy variable. So if you have other constraints, like x1 greater than 2, you have to introduce another dummy variable, which means an additional derivative and an additional equation. this is another complication. If you have a few constraints, this is fine. But if you have a multitude of constraints, then it becomes, you know, complicated. Okay. Now let me introduce another, I think, interesting consideration related to how to deal with inequality constraints. So let's suppose that I have a benefit function defined, nbx, x capital X. And let's suppose that we have a constraint of the type gx greater or equal than b. And for instance, the constraint would be x1 plus x2 plus, less or equal than b, plus x3 minus or equal than q. This is more reasonable because it's true, as I anticipated last time in my last lecture, it's true that usually we have convenience in using all the water that we have available. But it's also true that in many cases, from a physical point of view, this is a much more reasonable constraint. Why should I use all the water if I can reach the maximum benefit with less water? So basically, if I put an equal sign here, I am focusing only on the solution that uses all the water. But there might be a solution that uses less water that is more convenient. This is possible. And therefore, this, from a physical point of view, this constraint is more reasonable. We can't use more water than it's available, but we can use less water. So why not? Okay, so how to deal with this type of constraint? This is not easy because, you know, we learned how to prove the Lagrangian when the constraint is an equality constraint. When it's inequality, we don't know how to do that. So basically, the first solution that comes to my mind is to find a workaround, because we already know how to deal with the equality constraints. If I were able to find a workaround, I would be able to continue to use the solution that I already know. So is it possible to find a workaround here? Yes, it's very simple, because I could introduce here an additional dummy variable so that gx plus b squared is equal, let me say, s squared is equal to b. This is the same thing. If you allow s to vary, this is the same thing. Why s squared, you ask me? Because I want this quantity to be positive. Because this is a, an inequality meaning less or equal than, and therefore I have to add a positive value here. I can't accept that s takes negative values if I didn't introduce the square here, and s assumes negative values, then the equality will be greater or equal than. So I can't accept that. If I want the inequality being expressed in the way that gx can be less or equal than b, then I have to use a positive variable quantity here. And if s is 0, I get the equality. If s is greater than 0, s squared is greater than 0, then I have the condition of less or equal, which is what I want to achieve. And this is fine because, for varying s, but I have one more additional variable. But that's fine. Let me write the Lagrangian in this way. L capital X lambda S is equal to MD capital X minus lambda, which multiplies Gx plus S squared minus B. The same thing is if you use the, instead of this general relationship here, you can use this one. Same thing. In this case, it becomes x1 plus x2 plus x3 plus s squared is equal to q. Same thing, doesn't change anything. The only thing that changes is that I have one additional variable. That is to say that this additional variable doesn't have any impact on the derivatives with respect to xi, with respect to x. Because you see, this variable is not multiplied, s is not multiplied by x. And therefore the derivatives with respect to x don't change. Even the derivative with respect to lambda, in principle, doesn't change. Because this derivative only repeats the constraint. So you get the constraint again expressed in this way. But I have one additional derivative, which is the derivative of f(x) lambda s with respect to s. And this is equal to minus 2 lambda s equal to 0. Which leads to lambda equal to 0 and s equal to 0. So basically what happens here? The situation, as I said, is unchanged with respect to the quality constraint, same derivatives, but there is one additional derivative. And this additional derivative is not related to the other equations. It just says that you have two possible solutions for when you equate this derivative to 0. And the two possible solutions are either lambda equal to 0 or s equal to 0. What does this mean? It's very easy to understand the meaning from a physical point of view. What does it mean if s is equal to 0? First, let's think of the original constraint. The original constraint says that you can use all the water or less than that. What means s equal to 0? Means that you are using all the water. So this is the first case. S equal to 0 means that this equation is telling you use of all the water on one hand. And then there is another solution. What does it mean, lambda equal to 0? Means that you don't have any constraint. Lambda equal to 0 in your Lagrangian means that you are just focusing on the net effect, which means that you don't impose any constraint. Is this reasonable? Yes, because if you want to use less water, you don't need to impose any constraint. If you want to use less water than it's available, there is no need to impose a constraint to the maximum usage of water. So what? So what? This additional equation is telling us just split all possible cases into categories, which you can obtain by 1. Using the quality constraint, and 2. Removing the constraint. This is what this equation is telling us. She tells, just try 2 possible solutions. First, use the quality constraint. Second, use less water. Indeed, if you think to a constraint where the constraint is that your water use can be equal to Q or less than that, this is just what I said. So, only 2 cases are possible. Either the sum of x1 plus x2 plus x3 is equal to Q, and then this means adopting the quality constraint s equal to 0, or the sum of x1 plus x2 plus x3 is less than Q, and therefore there is no reason to introduce the constraint. So you may ask me, from a practical point of view, what should I do? And my answer is, you have to solve the problem twice. First, use the quality constraint and find a solution, or the solutions. Second, remove the constraint and again find the solutions. And then you compare the benefits, the resulting benefits, and you take the maximum. Is this clear? This is a subject, a question that, you know, it's, I tend not to exaggerate, but it's something that I ask at the exam, so I just wanted to tell you. I don't want to induce concerns, just pointing out. We will make, I told you to bring the PC because I want to make some exercise with the PC, and of course the exercise will help you to clarify the situation. Okay. So we solved also the problem of the inequality constraints, but what I want to emphasize is that any inequality constraint involves double work with respect to inequality constraint, because it involves to separate solution and the subsequent comparison of the results. By the way, there is one thing that I want to anticipate to you, so I take the opportunity to make a 1-minute break. And this issue issues are part of the very classical treatment of water resources management. Basically, the classical treatment, I'm not dealing with it anymore. But I kept some of the questions, of the practical questions in my course plan, because I think that it's useful that you know what are the advantages and the drawbacks of the analytical solutions. I already mentioned to you that analytical solutions are not much used today, but they are still interesting. I think they are interesting to understand, to gain a better understanding of the physical features of the problem. So this is something that I want to keep, because when you concentrate your attention on the analytical solution, you reach a better understanding with respect to using the PC, where of course you are happier because it's faster and it allows you to make very complicated computations, but very often by working on the codes on the PC, you lose the connection with the physics of the problem, which is important, because we are engineers, and therefore, I was saying, and therefore we need to keep always an eye on the practicality of the problem we are dealing with. And these classical subjects of water resources management are dealt with in a famous book that was written in 1980 by Peter Rauch. Peter Rauch was one of the first eminent water resources managers, because water resources management began its history, as I said, at the end of the 60s in the United States. And there were some persons who dedicated their attention, the first persons who dedicated their attention to this topic. Okay, Peter Rauch wrote this book, which is a very important book, a very useful reference, but I didn't suggest the book to you because it's no more actual today, it's not up to date. But by the way, Peter Rauch will visit, is 84 now, but he's in a good shape, and will visit us in June and will give a seminar to the students. And I will remind you the date, because I think it's an interesting opportunity to meet a person that really represents the history of water resources management. And he will give a seminar. I have to tell you, I must admit that he's not a good speaker, meaning that he's understandable, very good English, because he worked at Cornell University, East Coast, so very good English. But the problem is that he's not a good speaker, he's very, maybe the age, but he's difficult to follow. And he's a bit, the tone is monotone, he's not a good speaker, but still I would recommend you to attend that seminar, because, it's an example of a person that will be on June 2nd, I think. He's getting here on May 30 and leaving on June 7, yes. So June 2nd, he will deliver this seminar, and I will let you know. Okay, I think it's a good opportunity, especially for students attending an international course. When you have opportunities to meet foreign professors, don't miss these opportunities. Even if you are not interested in the subject, especially experienced professors who taught at Cornell, at Columbia, if you have these opportunities, it's always better to take advantage of them. Last year in this course I invited one professor from Canada to teach for 6 hours. At the end the students were not really happy because it was difficult to understand the English. So sometimes this happens. If a professor is not a native speaker, the English is much worse, but maybe it's easier to understand with respect to a native speaker who speaks a very good English, but sometimes speaks very fast, and it's difficult. But it's anyway a good experience. Okay, now let me start with a final consideration on the method of the Lagrange multipliers, and then I move forward. And the final consideration is related to the value of lambda, because you may remember that last time I told you, one question is, what is the value of lambda? And then when I solved my first exercise, I told you, look, now we have a relationship that gives to you the value of lambda. So from a mathematical point of view, you have no doubt that the lambda should assume a precise value which gives to the Lagrangian the right penalty. I told you, if lambda is too high, the penalty is too significant, too much. Conversely, if it's too low, the penalty is not enough. There must be an optimal value for lambda. And then we found a relationship for lambda in the practical exercise that I developed, and I told you, now you see that you have a precise value for lambda, a numerical value. But I told you, you are still not convinced from a physical point of view what is the meaning of lambda, what is the right value. Numerically, you know that there is a right value, but physically, you can't describe what is the right value. Now, I want to make a consideration to explain to you what is the value of lambda from a physical point of view, in practice. Okay? And then to do that, I need to rewrite the Lagrangian with a clean blackboard. So allow me to clean the blackboard and write again the Lagrangian. Okay, so the Lagrangian is given by L x lambda is equal to the net benefit and the x minus lambda, which multiplies. Let me make the case of the three allocation. I equal 1, 3, xi minus q. So I kept the net benefit in the generic form, while for the penalty, I think it's clearer if I refer to a problem with three allocations and a constraint, an equality constraint with respect to the three allocations. Okay. Now, if I wanted to write the dl, so dl x lambda, basically the del is the differential del, the total differential del. How should I compute it? First of all, L depends on x and lambda, so to compute the L, I have to compute the derivative of partial derivative of L x lambda with respect to x I, and this is summed for I equal 1 to 3 in dxi plus the partial derivative of L x lambda with respect to lambda in d lambda. And now, let's assume that we are on the optimum here. So I want to compute this total differential of the Lagrangian on the optimum, and therefore this total differential is 0. So let's suppose if I could identify a graph of L with respect to x lambda, if I am in the optimum, the total differential is 0. Of course, this is a graph which is not really meaningful because I have more dependent variables. This is a graph in 2 dimensions. It is indeed a graph in more than 2 dimensions, but let me just clarify what is the reason why I put the total differential to 0, because I want to compute it here in the optimum. Okay, then let's compute these derivatives then. And therefore, first of all, the derivative of the Lagrangian with respect to xi is given by, so let me write here, is given by the derivative of mdx with respect to xi, and here we have the summation, in the xi minus lambda in the xi. And the summation, just to be clear, I put a square parenthesis here. And then there is the derivative of Lxi with respect to lambda in the lambda. And this derivative basically is given by the summation for I equal 1 to 3 of xi minus q in the lambda. And this is equal to 0. Good. Now, this is the constraint. Let me assume that in correspondence of the optimum, the constraint is satisfied. So let me assume that this is 0. So let's assume that the constraint is satisfied, okay? Of course, you may say, who tells me that it's satisfied? Maybe not. Let's assume that it is, because this is what we want. We want the constraint be satisfied, of course. So let's assume that it is. Okay, so this is an assumption. Look, what could be the reason for the constraint not to be satisfied? A wrong value of lambda of the penalty. If the penalty is badly specified, you may end up with a solution that doesn't meet the constraint, but you don't want this. So let me assume that it is satisfied, okay? Okay, so if my assumption is correct, then we can work on this part of this relationship which is equal to 0. And look, the summation of the derivative of the benefit with respect to each decision variable times infinitesimal increment of the decision variable itself, this is the MV, total differential of MVx minus lambda. Here there is a summation, sorry for this. Here there is a summation because basically it's this one. Minus lambda, which multiplies what? The x1 plus the x2 plus the x3, please.
The summation is not outside?
The summation is not?
Outside.
Yes, it should be outside, sorry for this, but because I skipped a step and I hope that we didn't pick up. This is constant. Yeah, it's outside. Oh, yeah, correct. It's outside, sorry for this. Very good. Okay, but in any case, so let me go back here. Minus lambda what? The dx1 plus dx2 plus dx3. So dx of any decision variable, what is that? It's then dq. Because if you are in correspondence of the optimum and you assume that the constraint is satisfied, it means that x1 plus x2 plus x3 is equal to q. At this stage, if you take dx1 plus dx2 plus dx3, it's equal to dq. But this is 0. And then what you find is that lambda is equal to LBx over dq, which is what we wanted to find. So, what is the value of lambda? What is the value of the penalty? The value of the penalty must be such that when the constraint is satisfied, assumption, when the constraint is satisfied, if you give some more water, meaning that you are violating the constraint, what happens? Your benefit increases. Okay? And then you have to introduce a penalty. What is the value of the penalty? Must be equal to the increase of the benefit.